In this lecture, we'll look at a quick example to analyze the one-stage op-amp that we've been looking at so far, and we'll try to put together as many of the datasheet components as possible, datasheet values as possible. So to start off with, this is the one-stage op-amp. Let us say that the op-amp is driving a load capacitance of 100 picofarad, and let us also say that the device parameters are as follows. Mu and Cox is 100 microamp per volt square. Mu P Cox is 50 microamp per volt square. Let us say that VTN is equal to VTP is equal to 1 volt and let us say that the supply voltage is 5 volts, and let us say that the minimum length possible for the PMOS and NMOS is 0.5 microns, and lambda n and lambda p is equal to 0.02 volt inverse for L-min. Let us start off with these numbers, and let us say that the sizes of the transistors are as follows. So M0 has a size of 10 over 0.5, all widths and lengths being in micrometers. The width over length of M1 is 20 over 0.5. M3 and M4 have a width over length of 40 over 0.5. And finally, let us say that VB0 was equal to 2 volts. So the first thing we can do is write down the expression for the voltages and currents of every device that we can analyze. Now, the first thing we will do is to find out the value of the current through M0, which is ID0. So that current is as follows. ID0 is half mu and Cox W over 0 into VB0 minus VTN the whole square. And this is clearly half into 100 microamp per volt squared times 10 over 0.5 into 2 minus 1 the whole square. So this current through M0 is equal to 1 milliampere. So this current is 1 milliampere. So now all the derived quantities will be placed in blue color. Now, of course, if that happens, as long as both M1 and M2 are in saturation, you will find that each of them has a current which is equal to half a milliampere. So ID1 is equal to ID2 is equal to 0.5 milliamperes. So you have a current of 0.5 milliamperes flowing through each of these half circuits. Based on this, we can calculate the value of the GMs of the different transistors. So let us calculate the value of GM1. GM1 is root of 2 mu and Cox W over L1 2 L1 into ID1. This is 2 into 100 micro into 20 by 0.5 into 0.5e minus 3. So this is clearly, if I were to make the actions, so 0.5 and this is root of 4 into 10 power minus 6, which is 2 millisiemens. So GM1 is equal to GM2 is equal to 2 millisiemens. Let us now calculate what the value of GM3 and GM4 is. GM3 or 4 is root of 2 into mu P C ox W over L, so which is 50 E minus 6 into the W over L of the PMOS transistors is 40 over 0.5 into 0.5 into 10 power minus 3. And this is clearly, so 0.5 and 0.5 get cancelled, and so this is root of 4 into 10 power minus 6. So this is also 2 millisiemens. Once we know these two numbers, we know the transconductance of the devices. Now let us calculate the output conductance of the devices. GDS2 is lambda n ID2. So this is 0.02 into ID2, which is 0.5 milliamperes, and this is 10 microsiemens. Similarly, GDS4 is lambda P ID4. This is also 10 microsiemens. Now we are in a position to start writing down the expressions for the various datasheet components of the op-amp. So the first component that we'll write down is the DC, also called the low frequency gain of the op-amp. This is nothing but GM1 over GDS2 plus GDS4. 1 over GDS2 plus GDS4 is nothing but RDS2 parallel RDS4. So this is 2 millisiemens over 10 microsiemens plus 10 microsiemens. So this is a gain of 100 volt per volt. So this is the DC gain of the op-amp. The second component we will look at is the unity gain frequency of the op-amp. So omega u is nothing but GM1 over CL. This is 2 millisiemens over 100 picofarad. So this is 2 into 10 power minus 3 over 10 power minus 10. So this is 20 megaradian per second. Of course, Fu is omega u over 2 pi. The third component that we'll write down, we will skip the dominant and non-dominant poles and zeros, because we do not know what the capacitance is at node X. Since we are not given anything there, we will assume that CL is the only capacitance of interest. So the next component that we can write down is the slew rate. So the positive and negative slew rate are both equal for the one stage op amp. This is nothing but ID0, which is the maximum current that can flow in and out of the op amp, over CL. So this is 1 milliamp over 100 picofarad. This is it is 10 power minus 3 over this is 10 power minus 3, 10 power minus 10, or 10 power 7 volts per second. Next, we will write down the input common mode range. So the minimum value of minimum is nothing but VGS1. So remember, quick reminder, so when the input common mode is minimum, so as you keep decreasing the input common mode, M1 continues to have VGS1 across its gate source, and the same with M2, and the voltage at the common source node keeps falling with the decrease in common mode, and finally M0 is at the edge of triode, and therefore the input common mode level at that point should be VGS1 plus VDSAT 0. Now VDSAT 0 is VGS 0 minus VT, so this is 2 minus 1, this is 1 volt, and VGS1 is given by VT, VTN plus root of 2ID1 mu Cox W over L1. So this is 1 plus square root of 2 into 0.5 into 10 power minus 3 over mu Cox is 100 into 10 power minus 6 into, so the width to length ratio of M1 and M2 is 20 over 0.5. So this is nothing but 1 plus square root of so this is 10 power minus 3, and this is 40 over 1, so this is 1 over 4, or 1.5 volts. So VGS1 is 1.5 volts, and therefore the input minimum common mode is 2.5 volts. What about the maximum input common mode? As we have seen before, as we start increasing the input common mode, the gate of M1 increases, but the drain of M1 stays constant at VDD minus VSG3, and therefore the limit is given by the point when M1 just goes into triode region. that happens at a voltage VDD minus VSG3. This is the voltage at the drain. The gate can go one threshold voltage above the drain. Now let us calculate what VSG3 is. So VSG3 is VTP plus root of 2ID3 over mu PC ox W over L3. So this is 1 plus root of 2 into 0.5 into 10 power minus 3 over 50 into 10 power minus 6 into 40 over 0.5 or into 80, and as it turns out this is also equal to 1.5 volts. Therefore, the maximum input common mode is given by 5 minus 1.5 plus 1 or 4.5 volts. So the input common mode can be anywhere between between 2.5 volts and 4.5 volts. So this is the input common mode range. What about the output common mode range? So the output common mode range can be calculated as follows. So the maximum output common mode is given by VDD minus VSD sat of 4. As we have seen, VSG3 is 1.5 volts, therefore, which is the same as VSG4. Therefore, VSD sat 4 is VGS VSG4 minus VT4. This is 5 minus 1.5 minus 1 or 4.5 volts. Of course, the minimum output common mode depends on the value of the input common mode. So that would happen when as the output common mode decreases, eventually the transistor M2 would go into triode region, and therefore that will happen when the drain voltage goes one threshold voltage below the gate. So this would happen VCM in minus VT4. This is VCM in minus 1 volt. Now the next quantity that we'll calculate is the input referred noise of the op-amp. As we have seen before, the input referred noise of the op-amp, so which we'll represent as En squared, this has two components. So this is 16 kT by 3 GM1 into 1 plus GM3 by GM1. The first quantity, the first portion represents the noise of the input transistors referred back to the input of the op-amp. The second quantity, this quantity, represents the noise of M3 and M4 referred back to the input. As you can see, the noise of M3 and M4 depend on GM3, but the overall transconductance of the op-amp, it depends on GM1, and therefore the input referred component depends on both of these. As we have seen, since GM3 is equal to GM1 is equal to 2 millisiemens, therefore En squared is GM1 into 2, and this happens to be equal to 2.208 into 10 power minus 17 volt square per hertz. Of course, we are always talking about the noise squared voltage density, so I'll make that explicit here. Finally, so the noise voltage density, which is En over root delta F, happens to be equal to 4.7 nanovolt per root hertz. So this is the input referred noise density of the op-amp. If you knew the mismatch characteristics, you could also calculate the mismatch characteristics. So there are two things that we have left uncharacterized. So those are mismatch and calculation of offset voltage. Since we did not specify a VT mismatch, we have not calculated the offset voltage. And of course, we had not specified the capacitance at node X, and this would allow us to calculate the non-dominant poles and zeros of the system. Finally, there are two more things to wrap up this analysis. So the CMRR and common mode gain of the op-amp. So let us directly write down the expression for the CMRR of the op-amp. As we know, the CMRR of the op-amp purely depends on the GM of the input device and the output resistance of the current source transistor. So to do that, so this is nothing but 1 plus 2GM R0, where R0 is the output resistance of the current source. So that is 1 plus 2GM into RDS0, and RDS0 is 1 over lambda n ID0, which is simply 1 over 0.02 times ID0, which is, as we can see from the original op-amp, it is 1 milliamp. And therefore, the output resistance of M0 is 50 kilo ohms. This means that the CMRR of the op-amp is equal to 1 plus 2 times 2 millisiemens times 50 kilo ohms, and this is 201. Last but not least, we need to look at what happens to the noise of M0, because that has not been covered so far. So let us briefly look at that. So this is the noise of the current source transistor. So in this particular case, let's assume that the output is short circuited to ground, so that you are trying to find out the short circuit current. Now, if the transistor M0 has a current ID0, IDN0, this current source now enters the node XY, and at XY IDN0 splits into 3 parts. So the 3 parts are: there is current flowing into the source of M1, there is current flowing into source of M2, and there is current flowing into drain of M0. The impedance looking up at the source of M1 is approximately 1 over GM1, which is a very low impedance node. The impedance looking up at the source of M2 presents an identical impedance 1 over GM2, which is equal to 1 over GM1. And finally, looking down to the drain of M0, you see a resistance R0, it sees an impedance RDS0, which is much larger than 1 over GM1. As you can see, RDS0 is 100 kilo ohms, and 1 over GM1 is approximately 500 ohms. So as you can see, all of the current flows up into the sources of M1 and M2, and half of the current flows through M1 and half of the current flows through M2. So this current splits equally between these 2 parts. These 2 currents are correlated, so you cannot use IDN0 squared. You have to calculate the total current while using the linear quantities. So there is a current N0 by 2 flowing through M1 and the same amount flowing through M2. Let us see what happens to the current flowing through M1. That current flows through M3 to create a small signal noise voltage, which I'll call Vxn, and that noise voltage causes a noise current to flow through M4. Now clearly, since M3 and M4 are identical, this noise is also IDN0 by 2, which is the same as this noise. Now let us look at the total output short circuit noise current. If you apply KCL at the output node, you find that ISCN is equal to 0, because the current entering the node from M4 is exactly equal to the current leaving the node into M2. Therefore, there is no current flowing into the short circuit. This means that the noise from M0 does not appear at the output. So this is a very important result. And consequently, it also does not appear in the input referred noise. Of the op amp. So as you can see, the noise of M0 appears through the transistors M1 and M2, but does not affect the output at all.